Next, I want to introduce you to something called the complex conjugates theorem. Remember that in the last lesson, we talked about irrational conjugates, things where we had a positive and a negative with a radical or a square root sign. Now we're going to talk about something similar, but with complex numbers, things that have the imaginary unit involved. So if a plus bi, an imaginary number, is a root of a function, then a minus bi, which is the complex conjugate of it. Remember that conjugates means that one has a positive and one has a negative, and that also has to have a root. So very similarly to our irrational solutions, complex solutions, ones that contain imaginary numbers, also come in pairs. So you will never have a single imaginary solution to a polynomial. So we want to go ahead and find all of the zeros of this polynomial. And I'm emphasizing the word all because now we're going to be looking for not just real solutions, rational or irrational. We are going to be looking for possibly imaginary solutions as well. So the first thing that we will do is we'll start off just like we do any other problem and try to solve by factoring. But I notice that I have 1, 2, 3, 4, 5 terms, too many to factor. So I'm going to use the rational roots theorem. So we are going to find the possible rational zeros and then use that to continue. So P over Q, remember from last time and the time before actually, is my constant, which is 8, and my lead coefficient, which is 1, is going to be my Q value. So I'm going to say that P is equal to 8 and its factors 1 and 8, 2 and 4, and Q is equal to 1, its factors, well, 1 and 1. So when I write this, just like I've been doing, since I only have Q of 1, I can write all of these as integers, plus and minus 1, 2, 4, and 8. So I have 8 possible rational zeros. Let's think about how many zeros we have to have total. We have to have, let's see, we have a 5th degree polynomial. So if we have a degree of 5, then that means that our n, the number of solutions, is also going to be 5. We're going to go ahead and speed this process up just a little bit and use either your calculator, or if you're at home, you can use Desmos if you don't have a calculator app or a physical calculator, and graph the polynomial to find the actual rational zeros. Because we have 5 actual solutions to find, we want to go ahead and speed this process up a little bit. I'm going to show you how to do it on the calculator. So this will be an emulation of the calculators we have in class. But again, you can easily put the polynomial into Desmos. Just type all of this in and it will give you the same information if you're at home. This is the calculator that is similar to the calculators we have in class. And what we want to do is go ahead and click on the y equals button up in the upper left corner, and we want to put our polynomial in. So we want to put this in. And in order to do that, we can use the X button that's on the calculator right under that green alpha button. And then in order to get the exponents, we want to click on the little up arrow, similar to what you would do on your keyboard on your computer or Chromebook. It's right under the clear button, kind of along the right-hand side. And then once you put the polynomial in, we want to graph it. So we want to click on the graph button. And we can see the points here on the graph on mine. On yours, if it's a little too unclear, what you can do is instead go to the table. And to do that, you hit Shift and then the graph key to get to a table. And what you will notice is that right around an x equals 0, because we want to be just one side or the other of the y-axis, I notice that I have a 0 for y at an x value of -1, and I also have a 0 for y at an x value of -2. So those are my solutions or my x-intercepts. Going back to the graph again, you can see that -1 right here. Notice that that's one of those bounces, so it's a repeated solution. And then at a +2 is our other solution. So let's go back to our notes and we'll continue from there. We found out from the calculator that our actual zeros, our x's, are -1, another -1, so I'm going to write it a second time to remember that that was my bounce solution, and a 2. So we have 3 real solutions that we can physically see on our graph. That means that in order to equal 5 total, I must have 2 imaginary solutions. And so we're going to have to find those solutions now. We have 3 of the 5 currently. So let's go ahead and use synthetic division to partially factor. So even though we know what 3 of our solutions are, we need to figure out what the remaining polynomial is once we pull out the associated factors, and then see what we can do with that remaining polynomial. So we're not off the hook on using our synthetic division, even though we kind of know what to expect with the result. We should get a remainder of 0, or you could think of it as if we are taking out a factor of, say in this case, an x plus 1. But remember, it's the solutions or the k values that we use for synthetic division. So let's go ahead and set that up. The first solution that I'm going to use, or the first k value, is a -1. And I'm going to give myself a pretty big synthetic division symbol here because I know I've got a lot of terms. And in fact, let's go look at all of those terms real quick. I want to check and see if I need any of those placeholder zeros. And sure enough, I do. I jump from a 5 to a 3. So I don't have an x to the 4th term. I do have a squared and a 1 and a 0. So I'm going to need to insert a plus 0x to the 4th power. So let's do that and then finish off the rest. I have a 1 in front of that, and then 1, -2, -12, and -8. We're going to do synthetic division here. Why don't you pause the video and then come back and check your work. All right. Once you have done your synthetic division, which I'm not going to go into in detail, we've done it enough that you should be able to do it pretty proficiently now. If not, go back and watch the videos on synthetic division. We should get that 0 remainder. So again, we know that x plus 1 is a factor, and this would be our remaining polynomial if we put it back together with its variables. However, I still have 1, 2, 3, 4, 5 terms in my polynomial, so I know I'm going to need to use synthetic division again. So rather than going ahead right here and writing my partially factored polynomial and then taking those same coefficients and rewriting them in another box for synthetic division, I'm just going to keep going. So let me show you this little trick. I'm going to just draw another box right underneath. It doesn't have to extend to include the 0 because remember that was our remainder. And I'm going to go ahead and divide by another -1. Remember that -1 occurred twice as a solution because it was a bounce. So I already have my coefficients written for me, and I can start doing my synthetic division. We will do this one more time with the 2 afterwards. So why don't you try doing -1 and then drawing yourself another box here and doing 2. Come back and see if you've got those zeros and just check all of your work, all of your positives and negatives and how you came out. All right, when you did synthetic division a second time, you're going to end up with 1, 2, 3, 4 terms and that 0 remainder. And we could check grouping on this. It might or might not work, but since I've already gotten the process down of doing synthetic division, let's just go ahead and use it one more time with the 2, like I mentioned. And again, we'll get a 0. And now we only have 3 terms, and one of those is a 0. We have definitely got this down to a much smaller polynomial. And so let's go ahead and begin the process of solving by first writing the factors that we have. I'm going to go ahead and come up here on the right. I've got enough room, but if you don't have about half of your page left, you may want to come down below instead. So I am going to solve now. And remember that when we are solving, we want to write all of our factors that we found so far and then whatever the leftover polynomial is. So I'm going to say x plus 1, because remember it's the opposite of the k value or the solution, another x plus 1, and then I have an x minus 2, and then finally what I have left over as my polynomial, well, let's see, constant x and x squared, so I'm going to have x squared and plus 4, and that's going to equal 0. So some of these I can go ahead and immediately solve. I know that x plus 1 will equal 0, so x is equal to negative 1. I already knew that from above. X plus 1 equals 0 again. X equals negative 1. Instead of writing this a second time, you just could note this one to be a repeated solution instead. Then I have x minus 2 equals 0, so x is equal to 2. All right, let's talk about what to do with this x squared plus 4. Now we know that if we have two terms and there's adding between them, remember we would be looking for perfect cubes, and we have perfect squares but not perfect cubes. So let me show you how we're going to deal with this. We're still going to solve it, but those imaginary numbers are going to come into play. So I'm going to come down here and rewrite x squared plus 4, and that needs to equal 0. Whenever I have a quadratic with only the first and last terms and no bx term in the middle, I typically would want to solve that with square roots. So I'm going to take the x squared and leave it, but say that that equals negative 4. Move the 4 over to the right by subtracting. And then I can take the square root of both sides because I know that the square root and the squared will cancel on that side. Here, I'll take the square root, and don't forget to put your plus and minus because we don't know if this was made up of two positives or two negatives, because once we square it, we can't tell anymore. The left side will simplify to an x, and then we're going to say plus or minus, and we need to deal with the square root of negative 4. Well, the square root of negative 4, we can take care of the negative, if we remember our skills from the previous chapter, by saying that it's an I on the outside, that imaginary unit, because remember that I is equal to the square root of negative 1. So I can say that it is a 2 times I, because I know that once I take that negative away, I'm just left with the square root of 4, which is 2. So we have our final two solutions now, and they are complex conjugates of each other, the positive and negative version of 2i. Now, I want you to notice that this is a sum of two squares, and we talked previously about not being able to factor a sum of two squares, only a difference of two squares. But that changes today. Now, let's make ourselves a note, because if I have solutions here, I have a positive and negative 2i, x is equal to that, then just like x is equal to negative 1, I can move to the other side and get a factor. So let's see what those factors are going to look like. I'm going to have factors that are x minus 2i when I bring a positive 2i over to the side with x, and then I'll have x plus 2i when I bring the negative 2i over to the other side. So notice how similar this looks to our difference of squares now. It's just that there's an I involved. So we can now factor a sum of two squares. Let's write ourselves a note about that. So if we have something in the form of a squared plus b squared, then we can factor it by saying a plus bi and a minus bi, which are complex conjugates of each other. So now, starting today, we know how to factor a sum of two squares.